Now we'll see what are double shift instructions. After previously we had seen what are shift AL, shift HL, and other different versions of shift instructions. Now we'll see what is double shift instruction. Double shift instruction is similar to the normal shift instruction. Only the highlight of this instruction is that in this, the instruction is provided with the basic operation, and that is needed to implement operations on long unaligned bit strings. Long unaligned means what? If the data is long, that is the data type is long, or the given string bit strings are long in what you say, size, memory. Okay, and if those given bit strings are unaligned means what? They are not properly or systematically arranged in a proper manner. They are just somehow scattered over here and there, so that is nothing but unaligned. So double shift instruction is basically used to what do you say, implement the operations on long unaligned bit strings. Okay, then the double shift operates either on a word, a double word, as follows. Okay, either on a word or a double word, and it operates on these operands, but how? In these following two manners. What are these two manners? Taking the two word operands as input and producing a one word output. Means what? Taking two word operands. There are two word operands, they will be as input and they will produce a one word output. Only one word. That means input is 2, output is 1. And second is taking two double word operand as input and producing a double word output. Means what? In first word is the input, two words are input, one word will be the output. In second is two double word operands is the input and a double word will be a output. Okay, only a single double word. Then after that, now over here see what is written. Of the two input operands, one may either be in a general register or in a memory. Okay, uh, whatever the two operands that are provided as input for the double shift instruction, out of those two, one operand may either be in a general register and one will be either in a memory. Okay, so while the other may only be in a general register, the results replace the memory or the register operands. The number of bits to be shifted is specified either in the CL register, whatever are the number of bits that you have to shift, that is shift by 1 byte, shift by 10 byte, that number of bits, no, it is specified in the CL register. Okay, or it can also be specified in a immediate byte of the instruction, either in a CL register or in a immediate byte of the instruction. Okay, the either of these two. Then what is the next point? Bits are shifted from the register operand. There is a register operand, and from that register operand, the bits are shifted. Where they are shifted? Into the memory or in the register operand. Clear? Whatever the bits that you have to shift them, that bits they are either in the register into the memory or the register operand. So what will happen now for the flag? The carry flag is set to the value of the last bit that is shifted. Whatever is the last bit that you are going to shift, that bit will be residing in the CF, or it will be carried to the CF flag. So what will happen? The CF flag will be set to 1. Okay, and shifted out of the destination operand. Okay, so SF, ZF and PF are set according to the value of the result. Now remaining flags, that is the sign flag, zero flag and parity flag, the status of these flags will be set depending on the result of the what is the of this instruction. Now how it will be happened? See, if the result is 0, your ZF flag will be set. If your result is a signed result, okay, negative or whatever it is, then the SF, that is the sign flag, will be set. And if your result is containing even number of ones, then it will set your PF flag, that is the parity flag. Now what will happen with the OF and AF? OF and AF, that is overflow and auxiliary carry flag, are left undefined because in this you are just shifting. So overflow and auxiliary flags are not at all changed, or they are not at all being disturbed. Okay. Now next we will see the shift left double. We saw shift left in the normal way, but now we are going to see in terms of double. Okay. So SHLD, we have the short form as SHLD. What happens in this we will see. Now we'll see what happens in this. This shift bits of the RM field, that is register or the memory field, to the left. Very simple. This instruction will shift the bits either of the memory or of the register field to the left side, while shifting the high order bits from the register field into the register or the memory field on the right side. Means what? Shifting will take place from uh, left side to right side. Okay. The result is stored back into the register or the memory operand, and the register field is not modified. Now in this diagram we will see memory. First, this is nothing but memory of the register. Fine, that is also our destination. Same is the case with the register is nothing but our source. Means what? From where is the shifting going to take place? From your source, that is your register. See, it can either be, source can either be your register or it can either be your memory. Okay. Now in this case what we are seeing, source is the register and destination is nothing but your memory of the register. How many we are seeing in terms of how much data type? Sorry, what data type? Double. So what is the destination size of our destination and source register? 0 to 31, that is 32 bit. Okay. Now over here CF is nothing but your carry flag. This carry flag, what it will do now we will see. Okay. Now the shifting will take place from source. It is taking place from how, means what it is going to do, it will shift the bits of the register or the memory field to the left. See, it is shifting to the, this is source. Now whatever is the MSB over here, whatever is the MSB over here, see, this is the LSB, least significant bit, this is the MSB. Now shifting of this bit is going to take place source, that is from the left side to the right side. Okay. And whatever will be your least significant bit over here, sorry, most significant bit over here, that will set your carry flag. Okay. Then again we will see same thing but the opposite way. Now see over here, your source is your register and your memory of register is your destination. Now in this case what is happening? In this case what is happening? See, source was below, destination was above. See, source was up, now here source is above, destination is below. Fine. Now you are going to shift the bits either of the register or of the memory field to the right, because it is a shift right double. You're going to shift to the right while shifting the low order bits. Low order means what? MSB. So this is nothing but your what? Low order. See, this is your low order. Now in this shift right double, you are shifting the bits from your LSB, least significant bit. Means what? While shifting low order bits from the register field into the memory of register field on the left side. Okay. So the LSB, lower order bit of the source, is getting shifted into the right direction. That is, the lower order bits are shifting from right side. Okay. And they are coming to, or they are going on the left side of the memory of the register. This is your left side of the destination. Okay. And the result is stored back into the RM operand, or RM operand means what? Memory of register operand. And the REG field is not modified. So REG field will be not modified, and whatever will be the operand over here, sorry, whatever will be the byte or bit over here, it will get carried in this CF flag. Now next is the Boolean operation instructions. Now what are Boolean operation instructions? They are basically nothing but and, or, XOR, not. Okay. And not means what? It will invert the bits into the specified operand to form a ones complement of the operand. Very simple. Not means what? Inversion will take place and ones complement will be formed to the given operand. Next is what? The not instruction is a unary operation. Whatever will be your not instruction, it is unary. Unary means single one operation that uses a single operand in a register or a memory. It will only use a single operand. No two operands will be used. So not has no effect on the flag. As it is used, see, as not is a unary operation, it is using a single operand, so it will have no effect on the flags. Then what about AND, OR and XOR instruction? These instructions, they will perform the standard logical operation, and will do ANDing, or will all, or will perform inclusive operation and exclusive OR operation. Okay, or will do inclusive OR and exclusive OR, and these instructions can use the following combinations. What are the combinations of the operands? They can use two register operands. You not will use only a single operand, whereas AND, OR and XOR, they will use two register operands, and then is a general register operand with a memory operand, or a immediate operand with either a general register operand or with a memory operand. Okay, and then what will happen? AND, OR and XOR clear the overflow and the carry flag and leave the auxiliary flag undefined. What it will do? It will clear. Clear means what? It will reset. Okay, it will reset your OF and CF flag, whereas auxiliary flag will be not affected, and your sign 0 and parity flags will get updated. Okay. Now the next we will see, that is rotate instructions. See, rotate instruction means what? Your data, whatever is your data, or the sequence of the byte, the contents will not get lost, only they will get rotated. In shift, what was happening? Carry was generated and there was a chance where the bits are getting lost. But in the rotate instruction, your bits are not lost, they are just rotating in the given desired manner, either from left, either to the right, either carry with left, or either carry through right. But they are rotating means what exactly is happening? See, rotate instruction will allow your bytes, or allow the bits in bytes, word and double word to be rotated. Okay, bits rotated out of an operand are not lost as in a shift. As I told you, the main difference is in rotate instruction your bits are not lost, whereas in your shift instruction the what do you say, bits are lost. Okay, but are circled. Rotation is nothing but taking place in a circular pattern. That is, they are circled back into the other end of the operand, just rotating. Okay, rare and rare and the what do you say, front. Okay, rotate affects only the carry and the overflow flag. Okay, CF may act as an extension to the operand in two of the rotate instruction. This point you will understand in the diagram that I'll show below. Allowing a bit to be isolated and then tested by a conditional jump instruction. Whatever is your in whatever will be the result in after you perform your rotation, the CF flag will be affected depending on what type it is actually performing. Okay, and that bit will be isolated, and that particular bit will be tested by a conditional jump, that is JC or JNC instruction. Okay, so the CF, that is the carry flag, always contains a value of the last bit that is rotated out. Remember, in rotate instruction, the CF flag is always and always affected. Okay, so whatever be your value, let it be 0 or let it be 1, the carry flag is always set, and as it is always set, the rotation will occur along with this CF flag only. Okay. So even if the instruction does not use this bit as an extension of the rotated operand, fine. Then in single bit rotates, OF, that is the overflow flag, is set if the operation changes the high order sign bit of the destination. Okay. And if the sign bit retains its original value, whatever is your sign bit, if it retains its original value, then your overflow flag is cleared. Fine. On multi-bit rotates, the value of the OF is always undefined. Whatever will be your overflow flag in terms of multi-bit rotation, your OF flag is undefined. Means what? It is not affected or it is not changed. Now we will see the first type of the rotate instruction, that is ROL, that is rotate left. Now we are rotating to the left side. What it is written over here? ROL will rotate the byte word or the double word destination operand left by 1 or by the number of bits specified in the count operand. Okay. Then an immediate value or the value contained in the CL register. For each rotation specified, whatever will be your rotation specified, the high order bit that exists from the left of the operand, it will return at the right to become the new lower order bit of the operand. Now what is the meaning of these four lines? See over here. You are going to rotate from where? You are going to rotate your data, that is your byte word or the double word destination operand, to the left by 1. It will either be by 1 or whatever will be the specified number of bits. Suppose rotate by 10 bits, rotate by 100 bits, whatever will be the specified number of bits, it will keep on rotating upon that specified value. So this is nothing but memory of your register, that is the destination. This is your low order, this is your high order, this is your carry flag. Now where you are going to move? Towards left. See the arrow is pointing. That means what? Your higher order bit is gone first to the carry flag. Okay. And then it is nothing but rotating slowly to the left order and coming to the start. That is, it is higher order. This higher order is rotated to the lower order. Okay. Exactly opposite will take place in ROR. ROR, what it will do? From, see, you have to rotate to the right. Means what? Whatever will be your byte word or the double word destination operand, it will rotate right by 1. Okay, it will rotate to the right. Now, see, this is your right side. Means what? Lower order is getting rotated and this lower order will be rotated and shifted to your higher order. Means what? Whatever is your bit over here, it will go to the carry flag. After getting to the carry flag, it will start if there is a carry generated, it will go to the carry flag and this result will be not result, this byte will be slowly rotated to the right and it will come to the what you say, MSB. It will come to the MSB, that is from right it will come to your left side. Okay. Then next, RCL, that is rotate through carry left. What happens in rotate through carry left? It will rotate your bits, okay, in byte, word or double word, destination operand left by 1 or by the number of bits that is specified in the count operand. Now that count operand can be an immediate value or the value that is contained in your CL register. Fine. Now in this the instruction differs. How it differs from the RCL means what? Rotate through carry left. And ROL means what? Rotate left. Now what is the difference between ROL and RCL as these both are rotating towards left side only? What is the major difference? See, in that it treats whatever is your carry flag. Okay, it treats the CF as a high order 1 bit extension of the destination operand. Fine. Means what? This will be treated itself as a high order bit. First, whatever is the bit over here, it will get rotated to the carry flag after it is getting rotated to the carry flag, the moving process or the rotating process will start from here itself. See the difference, huh? See, first what it was doing, suppose whatever is the last bit over here, it will start rotating. This bit, suppose over here we have 1. This 1 will be gone to CF flag, okay, and this will be treated as isolated bit. This will be treated as isolated bit, and this bit will not be counted in your rotation. Rather, your rotation will take place from here itself, from the middle only. It will take place from here itself. But what will happen in rotate through carry? In this, whatever is your last bit, that last bit will be first uh, given to or will be assigned to your CF flag, that is the carry flag, and along with the carry flag the rotation will take place. Means what? Rotation will be carried through rotation will be taken place, including your carry flag also. Over here see the direction. In rotate, normal rotate, your rotation was taking place from this middle part itself. That is, once you assign the last bit, the rotation was taking from here itself, from the middle part. But now the arrow, first the bit will be shifted to the carry flag. After it is shifted to the carry flag, then from over here it will start rotating and it will come to the 0, that is LSB position. Just see the difference. The difference is of this arrow. This CF is getting rotated from here, whereas in ROL it was getting rotated from this middle only. Okay. Then same is the case with RCR. Just the direction is changed. Over here we were doing from left side, and now we are doing here from right side. That's it. Means what it is happening? This instruction, the carry flag, the carry flag is treated as the lower order bit. Okay, this will be your now lower order bit, and the extension of the destination operand will be taken, and the lower order bit will exist from the right side, and it will slowly move, and it will return to your higher order bit. Okay, I hope now this RCR and this is rotation instructions are clear. Now we will see what is byte set on condition instruction. That is nothing but short form of this is setcc. Now what is this setcc? This group of instructions sets a byte to 0 or 1, whatever will be your, means whatever, whenever this instruction is used or executed, this group of instruction will set your byte to 0 or 1. That's it, depending on any of the 16 conditions that are defined by the status flag. Whatever be your whatever be the condition of your 16 status flags, this setcc instruction will set your byte either to 0 or 1, depending on the status of your flags. So the byte may be in a memory, or it may be a 1 byte general register. As usual, the byte may be in the memory or it will be in a general register. So these instructions are especially useful for implementing the Boolean expressions. Means what? This setcc is mostly used in Boolean expressions in high level languages such as Pascal. Okay. Now setcc is the instruction that is set byte on condition cc. It will set a byte to 1 if the condition cc is true. Whatever is your given condition, if it is true, if it is it will set to 1 if the condition is true, and if your condition is false, then setcc will be assigned to 0. Fine. Now the last instruction is the test instruction. What is the test instruction? Test is nothing but a mechanism that is used to test itself. Okay, so it will perform the logical and of the two operands, clears the overflow flag and carry flag, and leaves the auxiliary flag undefined, and updates the SF, ZF and TF flag. So what is important in this test instruction? Test instruction will perform the logical ANDing of two operands. That is the main key point to remember. Logical ANDing is performed. Then the flags can be tested by conditional control transfer instructions or by the setcc instructions. Means what? A very very important thing is that you can use this test instruction only after the implement execution or implementation of this setcc. Or without setcc you cannot use this test instruction. It is clearly mentioned over here. See, the operands over the flags can be tested by conditional control transfer instructions or by the set byte set on condition instructions. These operands may be word, double word, word or byte. The difference between test and logical and is that test does not alter the destination operand. Alter means what? To update or modify. And what does logical ANDing do? Logical ANDing will actually alter or modify your destination operand. Okay. So the test differs from the BT. BT is your instruction, bit instructions. In that, test is useful for testing the value of multiple bits in one operation, and the BT, whereas the BT tests a single bit only. Test will, what this test instruction will do, it is useful for testing the multiple bits, but your bt instruction is useful only when you have to test a single bit only. Okay, so this is nothing, these all were your logical instructions. I hope you all have understood. So thank you.